Hey folks, Todd Coburn here with the Aerospace Structures series. This is our last sub-video for Lecture 1 for Dynamics. And in this video we're going to cover a couple additional topics. Let's take a look at what's important. Okay, we talked already about forces and we talked about masses, okay? In SI units, the units of mass and force and acceleration, they're fairly easy to understand. In the US units, the idea of pound mass and pound force, two things with the same name. We talk about forces, I weigh such and such pounds, and yet we also talk about our mass as if it's pounds. And to make that clearer, a lot of times in engineering we'll call it pound mass versus pound force. They're really the same thing. If I say I weigh 200 pounds, that means the earth is pulling on me with 200 pounds and I am pushing and I am pulling back on the earth with 200 pounds. We've got this vector that between us of attraction of that amount, of force. However, I also happen to weigh 200 pound mass. So the idea of pound mass is, it basically is a way of talking about mass, but using a little different unit, which actually perfectly matches the force unit. Now when we start talking with dynamics, and we get away with that a lot in statics and with a lot of analysis out there in industry. In dynamics, we have to be a little more careful because if we're doing acceleration and velocities and things, we need to use slugs for our mass unit for most calculations unless we're a little bit careful, okay? So we can talk about this a little bit since we use pounds so much in industry. You want to remember a pound mass weighs 1 pound force at sea level. That's basically its definition, okay? And that means it's because the acceleration of gravity changes with elevation. That means that will be different. You're going to have the same pound mass, but the way that equates is a little differently. Let's take a look. For example, the Earth has a almost 4,000 mile radius. Everest is 29,000 feet high. Typical aircraft cruises at 41,000 feet. So if we look at an aircraft flying 41,000 feet above Mount Everest, we actually would get a G of 0.993, the acceleration of gravity at sea level. That's not nothing, but it's actually so small it's actually not going to be meaningful in a lot of engineering calculations. This little equation that we can derive from Newton's law of gravitation is one convenient way of converting what the acceleration of gravity is at two different elevations. Now remember, the r that we're sticking in here is not just the distance from the surface of the Earth, it's the distance from the center of the Earth. So you need to take the radius of the Earth and add any other elevation to get both your R1 and R2, okay? So if we have something here at sea level, we'd plug in the radius of the Earth top and bottom, and we'd get that the G where we are is the same as the G on the surface of the Earth. If we want to talk about the acceleration of gravity, how much it pulls on us on the top of Everest, we would have to put in the radius of the Earth plus the radius of Everest in the one calculation in our R2, and put in the radius of the Earth in R1, and that would give us that acceleration of gravity at that elevation. So that's kind of a convenient little calculation that we can use. And a lot of times what we'll also do in industry, in aerospace anyways, is we'll take, since F equals mg, mass times gravity, and the acceleration, you have to use units of slugs to use this unless you talk about our acceleration in g's, like how many times the acceleration of gravity. In this case, you can just plug in your weight times the number of g's, and that will give you what that number is. For example, if you want to know how much force is on an aircraft, you can say, well, I'm pulling 2 g's, so you just multiply the weight of the aircraft times that 2 g's, and that will give you the force that's being applied. Kind of sloppy, but it works. Okay? Next idea. So when we're dealing with calculating gravity, we can actually use our latitude. You can plug in the latitude, like in degrees, plug that into this formula, and that will tell you what the acceleration of gravity is at that latitude. So that's kind of a convenient way of converting, and this shows it plotted how your gravity changes as a function of latitude. Okay, so that's kind of a curious little helpful item for a few problems that we're going to run into when we're dealing with the law of gravitation. Now, this and the next few slides we already covered in statics, so I'm going to stick a link. Watch for the link here, and if you need a review on how to add vectors, I'm going to send you back to our statics discussion. Okay, all of this is old news, stuff that we should have known all the way back from physics, but we covered it in statics. It's critical that you understand that this for three-dimensional vectors. We covered that in statics. Watch for the link at the top if you need to review dot products, cross products, and those kind of things. Also, if you want to, so when we're taking a cross product, there's a cool little graphic and idea that I came up with that I actually talk about in detail. It goes back to the idea of all this cross product is you following a right-hand rule. So when you have an I cross with I, you're going to use right-hand rule. So I cross with I is going to give you nothing because your vector is always going to be perpendicular. I cross with J, you jab your fingers in the I, wrap them toward the J, and that tells you you're positive K. I'm going to, in other books, come up with another method that's less clear in my opinion. I'm going to send you back to my statics video. Look for the link right at the top. Go watch that if you need to review how to do cross products. Also triple products. I'm going to send you to another vector for that. Also for mixed triple product, I'm going to send you to another video for that where we already covered this. Okay? All right. Next idea is sketching the problem. We already talked about sketching the problem. It's critical to sketch your problem out. This, if we have a problem like this, Beer and Johnson calls this a space diagram. I call it a sketch, no problem. And then turning that into an engineering problem we can solve into a free body diagram by just taking this critical point, drawing the three vector forces, acting on the point. This is very useful. We covered this in statics also. Let's practice a little bit. What happens if the sum of forces acting on a rocket is 50,000 pounds? So imagine a rocket. We've summed up all the forces. We get a net value of 50,000. Well, you're going to see an acceleration, right? Due to F equals ma. Force equals mass times acceleration. If you have a net force, you're going to get an acceleration. How about we have the sum of the vertical forces on aircraft are 0. Is that aircraft going to drop? No. Its vertical position will remain unchanged because the sum of the forces is 0. Remember, the reason an aircraft falls to the ground without some kind of lift force pulling it away is because the net force is actually pulling toward the ground. If the net force, vertical force is 0, it's going to not change its vertical position. That means it's probably flying fast enough that its lift force is perfectly balancing its weight. What happens if the sum of vertical forces, however, is plus 40,000 pounds? Well, now we're going to get a vertical acceleration, right? What happens if you stand really close to a huge football lineman? Well, Newton's law of gravitation says because he has mass and you have mass, you guys are going to feel some love. You're going to feel some attraction, an attractive force between the two of you. You might also notice some other things. How do you determine the magnitude of the attractive force toward that football lineman? Well, you'd apply Newton's law of gravitation, right? You take his mass and your mass, you take the distance between you squared and multiply by the constant of gravitation, and then be really careful with the units to make sure that they all cancel out so you're getting an acceleration of feet per second squared kind of number. Let's say an aircraft weighs 150,000 pounds at sea level. What's its mass? It's pound mass. Well, pound mass is the same as pound force. It's got the same magnitude, and therefore it's going to be 150,000 pound masses. What is, if this aircraft flies to 35,000 feet, its mass remains unchanged. In fact, the force remains nearly unchanged. It hardly changes because gravity hardly changes at that elevation. What's the acceleration of gravity at 35,000 feet? Well, you can plug in your values in the equation we provided earlier, but it's going to be a hair under g. If you want to know how much, you can plug into this equation, and that will give it to you. Make sense? So we covered a couple additional little tweaks on what we saw before in terms of the law of gravitation. We kind of flew through some old statics vector stuff. It's reminding you that you need to know this, but I'm going to send you back to those statics videos. Be sure you watch all the videos for this lecture in order. Go back and review any pieces of statics that you need to move forward, and then move forward with confidence because we're getting into more of the cool stuff in dynamics.